afternoon and welcome. My name is Alex McDonald and I'm the chair of SNIA Europe, and also I work for NetApp. Does anybody work for NetApp here? Nobody works for NetApp. That's really reassuring, so I can say what I like. So, before we go any further, I just want to ask, how many of you consider yourself to be software engineers? How many of you have a family who consider you being a software engineer? How many of you can fix a laptop? No, a few, okay. But I bet you didn't know this. I want you to tell me how many nanoseconds it takes for an electron to get from the top of that piece of... Remember Michael talking about plug compatibility, by the way. It's only plug compatible at this end. This end is a UK 0.6 times the speed of light, which really doesn't answer the question. It's 3 nanoseconds. That's an excellent answer. You know, you're the first person to have actually correctly guessed how long it takes an electron to travel from one end of that plug to the other. Seriously. I mean, I've had all sorts of guesses, like 3 light years and, you know, how tall are you anyway, and all that sort of stuff. But I just want to point out that's 3 nanoseconds, and that 3 nanoseconds is going to become relatively important because we must start talking about numbers that are exceedingly, exceedingly small, or exceedingly big, depending on your point of view. If you're an electron, they're all huge, but if you're me, they're all relatively small. That's 3 nanoseconds. My great heroine, Grace Hopper, who invented the COBOL programming language and was active in the late 50s and early 60s. She used to hand out 11-inch pieces of wire to her audience and say, that's a nanosecond. And people will go away with an 11-inch piece of wire to represent a nanosecond. And it's actually quite an interesting concept when you think about it. It's not instantaneous. It's hugely fast, but it's finite. And that's the problem that we have. And that's where persistent memory becomes interesting. That, by the way, is the plug at the end of this. I've got to point this out. That's a Brexit plug, okay? I see the politics even gets this far. Right? This is in the form of a brief introduction and highlights some of the points I just want to make about persistent memory. This is not an in-depth tech dive because there's just too much to talk about. I'll point out the websites that we have on the SNIA website where you can get huge amounts of information about persistent memory in all its forms, shapes, sizes, and how to program for it. Actually, we ought to get that man a prize. I don't know what, an extra sandwich or something for coming up with 3 nanoseconds. I'm really impressed by that. Deeply impressed. Yeah, his answer's also correct, but it wasn't really the answer I was looking for, was it? You know, you think he's a plant, don't you? You know him. That's even worse. So this is a brief introduction. I want to go back to the diagram that Michael showed up here. Okay, storage I/O currently is slow, big, and cheap. We know that. The last time I bought a hard drive was actually quite some time ago. I actually bought an SSD recently. And I paid around about, I suppose, $120 for a terabyte of SSD, which is, you know, not that expensive, and it's pretty big, and boy, is it fast. But it's only fast by comparison with what went before it, which was basically a couple of rotating bits of tin and a thing that swept it now and again and went, nope, it's not there. No, definitely not there. DRAM, main memory, is small, fast, and hugely expensive, although DRAM prices are falling. There's a bit of a glut at the moment of DRAM production. But things like machine learning, big data, IoT, in fact, just about everything demands nanosecond-type latencies and petabyte scale. In other words, the worst of both possible worlds in that you're at opposite ends of the spectrum. And there's a layer missing. And the layer that's missing is, remember that nanosecond? It's about that much a nanosecond. In a nanosecond, that's about the cycle time of DRAM in terms of putting in from DRAM. So you can actually do something in a nanosecond, thereabouts. And then you've got the scary thing about powers of 10. People tend to look at logarithmic scales and think they're linear, and diagrams like this persuade you that they are linear. In fact, these are not linear. And if this 10 to the 6 was to be represented in the same scale, you know this anyway, don't you? It'd be out the side of the building, all the way to Mars. So there's a real problem here in terms of scale, and there's a bit missing. And the bit that's missing is the bit between DRAM and NVDIMMs, and I'll explain what they are in a minute, and performance SSDs, which come in at around about 10 to the 4 nanoseconds, which is in sort of 10 microsecond range, or thereabouts, or thereabouts. All these things are within some margin of error. So there's a bit missing in the middle. And that missing bit in the middle is the bit that we've always wanted to fill, because there's another rule of programming. I don't know whether you know this, but all programming is an exercise in caching. Okay? Remember that. Next time you look at a piece of code, think to yourself, where did the data come to and go from? All programming is an exercise in caching. I didn't think of it, which is why it's smart. And this is all about caching. And these factors of 10 also apply in terms of the amount you really need at each layer to make optimum use of them in terms of their cost, their performance. And if you think about it, this needs to be about 10 times that in terms of the cache, and that needs to be about 10 times this, and so on. 10 times at each layer seems to be the sort of optimal rule of thumb in terms of caching. And this is all about caching. Would we do it all in DRAM if we could? The answer is no, because it's not persistent. Turn the power off, everything disappears. Although when I was a boy, actually I wasn't a boy, I think I was older than that. Anyone remember IBM System 360? Yeah, the 3 people in here, and the rest of you are probably lying. There are some old guys in here, I know there are. Okay. Core memory was persistent. We already had persistent memory. And one of the great problems in rebooting an IBM mainframe was to actually get it to reboot. Because very often when you just powered it back on, it went, oh, I'll just carry on from where, where I left off wasn't so good. And it failed. You got continual rotating failures. And there was a mechanism for getting around that, and it was all due to the fact that the core was persistent. So this is a non-persistent layer. So having it all as DRAM is really not what you want to do at all. Fast, but not very meaningful. So the kind of target application areas we've got for that fast middle layer of storage, the bit that's missing, the bit that goes from about 10 nanoseconds to a microsecond. We can do various things with it. And I think the one thing that's really important here about the kind of applications we're looking at are the kind of things that we currently do, but we don't do fast enough. How many of you know about dealing desks, traders, financial stuff? Do you know that they'd like it to go a lot faster? They would actually like to do it in nanoseconds rather than the milliseconds it's currently done in, because in a millisecond you can lose a trade. Money markets can move very rapidly, very small percentages, tiny, tiny, tiny percentages. But if you do enough of those little tiny percentages, they all add up at the end of the day. And doing them really quickly is something traders would like to do. And I was involved in installing a trading system where the trading system was some of the fastest, smartest, quickest kit you've ever seen. And it was all on the trader's desk, because we couldn't put the storage much further away because of the latency. Because every 10 meters of fiber optic cable was a lot of nanoseconds. And it just gets worse and worse. So all the things we wanted to do, and some things that we haven't done yet properly, but will be doing more of, things like artificial intelligence. And I'd encourage you to come to my talk tomorrow, when I'm going to be talking about what the kind of research that NetApp are looking at in terms of artificial intelligence and what we're using it for. And why nanosecond latency is important as a consequence. And some of these is to do with speed of getting access to your data, and some of it is to do with the sheer volume of the stuff. I mean, AI consumes ridiculous quantities of data and needs to do so really quickly. So I think we can all think of applications for this kind of intermediate layer of persistent memory. So what is interesting about persistent memory, though, is it's not like storage. Although it persists, it's not storage. And if I ever hear anybody calling it storage class memory, I will be taking them outside, to be quite frank, finding a very tall building to drop you off. Storage class memory is not what it is. How many of you have been tempted to say it? Go on, I dare you. No, I dare you. I dare you. Not now. Wise man. Storage class memory is not it. Persistent memory. The whole point about it is it's memory. It's byte addressable. This is not block addressed storage. This is not like disk, where the minimum size that you go out. Let's say we're updating, I move house, so my address changes. How long is an address line? 200 bytes, thereabouts, for a couple of address lines. Let's say 256 bytes. Let's be generous, 512. And when we go out to a modern database, we may be updating a page that's 4K, and then we're reading and writing that data from disk in 4K chunks. And that's an awful lot of data to move around just to change 512 bytes. Well, imagine you're doing it on a credit card transaction or microtransactions. These are the new things that are causing us real headaches. Come on, guys, sit down. You're welcome. Or there's stuff over there if you're hungry. There's the food you came for, it's at the back. All this is better than I am. So I was talking to a guy the other day about the Internet of Transactions, very small micro-transactions. We're talking about fractions of a unit of currency, really, really small things. Now, updating loads and loads of those on something that's not byte addressable is a really expensive exercise. Can you imagine you're doing a 4K in and out, having to do two-phase commit on these big chunks, stuff. This is byte addressable. You can do load and store. But it's persistent like storage. In other words, that once you've done it, it's done. It's actually committed to the storage interface. And I'll show you how it's exposed by the programming model. Anybody going to the hackathon next door? There's a persistent memory hackathon going on. So they can show you exactly what the NVM programming model is about. But I'll talk a little bit. So what it isn't, doesn't speak in blocks, isn't a disk, is not being addressed in large chunks. And it's also not something that's too slow for load and store access. Though I will talk a little about the fact that sometimes you do have issues when things are really, really quick, like a nanosecond to do a load or a store. If you're doing it to persistent memory and it takes 10 to 100 times longer, that might be a problem, but I'll talk a little about that in a second. So, it's not something that would normally stall the CPU waiting for a load to complete. Now, do you remember that thing I said earlier when I went, remember, all programming is an exercise in caching? And that's the reason why. CPU resource has always been relatively expensive. And making maximum use of it means that we will want to multitask, multi-process, multi-everything. When I was a lad again, System 360s, you ran these things flat out, literally 100%, flat out. 7 days a week, 365 days a year. And stalling a CPU and waiting for something is something you really don't want to do. It's a waste of processing time. The other thing that I learned in mainframe days, and this is another one, I didn't invent this, but this is one of those things we think, that is really smart. Every second that passes is a second you don't get back. And in computing terms, that's actually quite critical, because if you think about making a CPU wait, every second that passes is a second you don't get back. It's gone. It's been wasted, disappeared. And that's why we do things like multitasking, multiprocessing, because we don't want to waste the CPU time. We don't want to waste time, in effect. So how does it look? So JEDEC, another standards body, nice people, and they designed NVDIMNs and NVDIMPs. And these things pass the smoke test, by the way. These are real NVDIMMs, and you can plug them into a motherboard, and they will not burst into flames. They're not supported by that motherboard. You know what a smoke test is, don't you? A smoke test is if you plug it in and it doesn't start smoking, So, I mean, that seriously, there are some of our small form factor guys, they spend all their time making sure they design a new form factor and an interface that you can plug the old one into the new one and it doesn't burst into flames. I mean, I know it sounds primitive, but hey, there you go. So NVDIMM ends are look like DRAM and are backed up by flash. We've already got these. And these are horrifically expensive because they've got both flash and DRAM. But they do provide you with persistence, and they provide you with latencies down, if you remember, about 10 to the 1 nanoseconds in terms of that logarithmic scale. NVDIMM-P, slightly different. NVDIMM-P, it talks to the persistent memory, and there's various types, and I'll talk a little about some of them in a second. Through a set of data buffers, but those data buffers are not our responsibility, they're the responsibility of that non-volatile DIMM unit. And they've got latency that's a bit larger, 10 to the 1 to 10 to the 2 to 10 to the 3 nanoseconds roughly. And they're also non-deterministic. Now what does that mean? That means unlike RAM, where you can guarantee that every access takes the same amount of time, and it's as regular as a heartbeat, NVDIMM-Ps might be non-deterministic in that one or two of your attempts to do a load restore might stall. They might actually take a little bit longer than normal. And again, that causes us a few issues, but there are ways around it. But it fits in this nice area here that we've had missing. And you can build them big. You can build them out into the terabyte higher range. I mean, you can build lots and lots of this stuff relatively cheaply. Well, hopefully relatively cheaply. I mean, the whole point of persistent memory is that hopefully it's cheaper than DRAM, but less expensive but more expensive than SSDs. So don't worry, your vendors of NVDIMM-P will make sure that that is the case. They will make sure it's more expensive than SSD, but less expensive than DRAM. Why? They want to sell you the stuff, and it's the only way of doing it. So his performance falls in that scale there, so its price is going to fall in exactly the same place. So, again, Michael talked about this ecosystem. People came together and said, we need to cope with this new stuff. And in particular, we need to cope with this new stuff because of the things I've been mentioning, like its non-deterministic nature. And also because we needed the hardware people to talk to the software people. We need operating systems to be able to understand, for instance, where the persistent memory is. Why? Well, it's not although we're addressing it as memory, it's not a uniform address space anymore. Some of it's DRAM, and it's really fast. And some of it is this slower stuff. It's still fast, but slower, but it's still memory. So we need some way of informing the operating system that it needs to partition up the memory into the slower stuff and the faster stuff and deal with it appropriately. But Windows and Linux all support NVDIMMs, the persistent memory of one form or another. And have for some time, actually. So it needs support, the hardware, and then the software side. And we'll talk a little about the software side. The one thing it says, application program support, that's one area where you can get away without changing applications. In-memory databases, for instance. If you've got an in-memory database that currently runs in DRAM, then putting it into persistent memory and making it 1,000 times larger is not beyond the wit of man. I mean, it's really quite easy to do. It doesn't require a huge amount of application changes. So, doing it without application modification, you can use it as a fast SSD. You can actually turn it back into a block. You put a driver over it and turn it back into a block device. Doesn't sound terribly smart, but it might be particularly effective when you're first looking at these kind of technologies. A really fast SSD might be something that is what you want from your for your application. And you can memory map them into DRAM. So that's the other thing you can do, is use memory mapping, because they support the operating system to do this, and simply memory map them into DRAM, and you effectively have files that you can... Who knows about memory mapping? MMAP. Yeah, I can't remember the Windows call's called. Create file mapping or something really long and Pascal-y. But basically, both operating systems have support for turning persistent memory into a memory map file. You can use PM as DAX. There's no paging here. It stands for direct access. So you directly access the persistent memory at that given address. You're just doing loads and stores. So you're building variables that are in, or structures that are in persistent memory. Or you could use PM as volatile capacity, as a big main memory. There might be vendor-specific features for supporting that. The best way of getting the support for all this is the PMDK library that's being spoken about at the persistent memory hackathon that's going on. The PMDK library provides you with all these mechanisms for using persistent memory. So you don't have to reinvent the wheel, because it is a fairly big wheel to reinvent. He's not here this week, but there's a gentleman called Andy Rudolph from Intel who has explained to me in dreadful detail, detail beyond the width of my small brain, I'm afraid, how much effort goes into building these persistent memory libraries and testing them. So there are, oh God, I didn't realize this had a build on it. Do beg your pardon, I don't like builds. They surprise me as much as they surprise you. There are new emerging memory types as well that are coming along. So the one you're probably aware of at the moment is 3D Crosspoint from Intel. That seems to be a fairly popular phone. In fact, Crosspoint as persistent memory was quite difficult for Intel to sell. So their first approach was to take this persistent byte addressable memory and package it up as an NVMe SSD drive called Optane. So if you ever come across an Optane, it's actually persistent memory that looks like an SSD. But there are various new technologies coming along, most of which I don't know about. In fact, all of which I don't know about. But basically, some of these have disadvantages and advantages. They all have one thing in common. They're all relatively fast, and they're all persistent, but they have differences in terms of where they are in their development cycles, how much they cost to fabricate. Some of them are really cheap to fabricate, but have poor yields, and some of them are very incredibly expensive to fabricate. And the foundry problems that you have are exacerbated. Another figure, by the way, I like big numbers. Do you know how much it costs to build a silicon fabrication foundry at the moment? Anyone guess how much it costs? $5 billion, give or take. Yeah. Yeah, 5 and 5. And probably 10 and 10, by the way. Because I don't know if you noticed, there's an awful lot of virus going around in the places where they make chips. Okay? So it's suddenly got more expensive to not only get stuff in there, but also get stuff out. But fabrication plants cost a huge amount of money. And most of the fabrication plants you're going to see doing this kind of thing will be moving from DRAM production to persistent memory production, which will cause a shortage of DRAM, so the price will go up, persistent memory prices will go down. All the vendors will go, oh, I think we've gone too far this direction, and they'll start refabricating back the way again, produce a lot more DRAM, so the price will go down, and persistent memory will go into shortage, and then we'll, oh, we should really be over here, But that's what stimulates demand and stimulates technology advances. And I'm all in favor of capitalism when it works for me. So, we've got ongoing hardware requirements as well to support this kind of stuff. This is now a non-uniform or a NUMA architecture. That's actually quite significant because we've been here before. And we've had lots of problems before with non-uniform memory architectures. There was a Silicon Graphics box that I used to work on that had such non-uniform memory architecture. It had 3 speeds of main memory in it. And if you thought programming was an exercise in caching, operational management was also an exercise in caching. I mean, it was a dreadful box to work with. We need an MMU redesign because memory management unit isn't really helping us here. The way that you put NVDIMMs into a system is they announce to the BIOS what address range they're occupying, and then the operating system can query the BIOS to get the address range to understand that. But there should be ways about the MMU actually knowing that it's addressing something that's persistent memory rather than DRAM. And that will come. We need faster CPU context switches. I've got the world's best joke coming up about this. Okay? So pay attention. And we've got this updated DDR that we require. DDR5 is real soon now. And that should, who laughed? Because they've been saying it back actually for the last 3 years. Sometimes standards get stuck, let's face it. And the particular DDR5 standard is pretty stuck at the moment. However, it may make it out shortly. We've got DDRT, which is a transactional form of DDR. And the reason for this is this non-uniformity, the fact that persistent memory has this non-uniform way of reacting in terms of its latency. So sometimes it's going to be consistently, and then it'll stall and then go off and back to. So that non-deterministic piece is quite critical. So, it reminded me of this, yes. No, let me do a joke first. I'll come back to you. This is the joke slide. Look, it's the slide with a joke on it. Right? There are only 3 hard problems in computer science. Number 0, cache management. Number 1, naming things. We're terrible at naming things. Number 1, off by 1 errors. And number 7, async callbacks. Okay? Now, this is the bit that's really difficult. If you've got non-deterministic main memory, and we're currently polling the stuff, because it takes a lot longer. So let's say we do a store. What happens during that store? You sit there. You know, it's a lot longer than we're accustomed to. And we're effectively doing a polling out across the bus to find out whether that thing's actually gone or not, because it's going to make its way through level 1 cache, level 2 cache, level 3 cache, and all the way out to the persistent memory. So we're effectively polling, saying, has it gone yet? Has it gone yet? Has it gone? And when it does go, you can get on with stuff. The alternative is to do this asynchronously and do a context switch. Now, a context switch takes... So a context switch is where you save the state of the CPU, go off, do something else, and then eventually when an interrupt comes through, you go back to what you were originally doing. But context switches cost hundreds of nanoseconds. So there are occasions where you won't want to do them because it's too expensive to do them, and you might as well just wait. Async callbacks are a pain in the... Who's ever dealt with async call? You know how much I/O is async callbacks? All of it. You know how much a pain in the butt it is? Huge. Async is the thing you don't want to do. Async is where you fire stuff off into the unknown, say, see you later, walk away, go over and do something else, and then come back and hope that async bit's happened. I mean, the big problem with async is performance, making sure you get the right kind of performance, and error recovery becomes like, you can get a PhD in this stuff. So SNIA has come up with this persistent memory programming model. Now, the thing I want to point out about this, about dealing with this interface and the library that it's generated, this is not an API. Forget it. This has nothing to do with APIs. This is a specification that you can then go and build an API for. And there have been two APIs built so far, one for Linux, one for Windows. Okay? It's not an API, it's a specification that tells you how things should work, what they should look like, and what kind of information each layer provides to the next, and how to get from one layer to the next. So it's not an API. And that's why that's a squiggly red line. There, that says this isn't an API. This is also not an API. This is just going straight through. You can see there's this squiggly red line that says it's not an API. There's some way, some magic, and the magic is provided by the API, but we're not specifying it, of getting between, for instance, the application right through to the memory direct in this case, or through a PM-aware file system in this case, or just a capable driver that makes these things look like SSDs. So there's a variety of mechanisms for getting to it. In 2019, we started these PM hackathons. There's one running here, the PMDK. There's lots of white papers. The future is what we're calling a remote programming model, because somebody thought that we've had NVMe and then NVMe OF for over fabrics. Somebody thought, well, we'll have persistent memory, we'll have PM OF. And do you remember that thing about naming things? The really difficult things in computing science is naming things. Well, PM OF just sounds like, PMOF, and it's horrible stuff. So we're going to do something, we don't know what we're going to call it, but remote persistent memory we're calling it at the moment. And we're going to update the current persistent programming model, persistent memory programming model. So, this is where we are today, 3D Crosspoint. This comes from a pair of analysts. But basically you can see if you put that on a logarithmic scale, the idea is that the cost and the capacity are linear over some scale. That one's a logarithmic one. And that 3D Crosspoint, or persistent memory, fits in the middle between SSDs and DRAM. I want to emphasize, by the way, why this is so exciting. That to that is a huge leap. It's enormous. Absolutely enormous. So going from DRAM to SSD is one of the biggest leaps you'll come across in terms of our storage and memory hierarchy. It's really huge. And that's why it's so exciting, getting that bit in the middle sorted, the 10 to 3 nanoseconds. How far does light travel down, or electron travel down a wire in 1 nanosecond? About that far. Okay, so I want you to do that 100 times longer. Okay, so it's probably within the bounds of this building to get out there. Now, we've been doing testing on very, very high-speed interfaces, and we're getting problems. We're getting problems moving stuff more than about 20 feet away, simply because the speed is light in this case. It's all fiber optic cables. We are having serious problems in building really low latency where the stuff is more than like 20 meters away or so. Okay? We're into real physics is a bitch territory here, I'm afraid. What's the future? Right, well, remember PMOF? The reason we don't like the OF bit is that we're not going to do this stuff over fabrics, because that's the wrong way of looking at it. What we're going to do is disaggregate everything. We're going to disaggregate, we've already done it to a degree. Think about it, you disaggregated disk drives from CPUs. So disk drives and CPUs are separate. Always have been. Networks connect the two. And even to a degree we've disaggregated networks as well. Now we're going to start disaggregating absolutely everything. Remember the computational storage pitch? That's a form of reverse disaggregation that really is disaggregation as well, though. Because what they're doing is, for instance, providing you with a computation as, I'm going to get this right, computational storage as a service, a CSS, that is, for instance, a board that does nothing except talk to storage and does compression for it. And that's disaggregated, because the thing it's doing the compressing on is not part of the thing that's doing the compressing. So this disaggregation is going to take place right across the memory sphere as well, and we're going to end up with this bit in the middle, and there are 3 competing technologies at the moment, and this is usual in this industry, where there are 3 competing technologies. It's like Game of Thrones. 2 will die. There's a 4th. Oh, C6. It's already dead. Yeah, it died ages ago. See? They're falling like flies. But it's like Game of Thrones. One of these will succeed. 3 of them won't. The interesting thing is that there are some pretty big companies. Gen Z is HPE. That's the big sponsor of that. And the CXL, the big sponsor of CXL is Intel. So, you know, the two I'm not going to get involved. I'm going to let the Goliaths fight it out. And then the open cappy guys in the middle going, hello. Yeah. In the long grass. That's doing a bit of service, isn't it? I would get slapped by Stephen Bates for that. Anyway, so these are the technologies that will connect memory to processors. And what you're going to see is processors are going to become a fairly abstract concept as well. We've already got CPUs. Can anyone name me another PU? A GPU. That's where we already disaggregated that bit. How about a TPU? Ever heard of TPUs? No. TPUs are tensor processing units and I'll talk about them tomorrow. By Amazon, by Google. How can you get it? It's like a USB cable, isn't it? I just inserted that one upside down. It's either Google or Amazon. By Google. And what tensor processing units are processing units that are specialized at doing one thing, and that's adding very, very quickly lots of very small floating point numbers. That's what they're really good at. That's disaggregated. And we're going to see a lot more disaggregation, and buses are going to become incredibly important. It's a really interesting thing that's going on here, and it's interesting watching how the industry is moving in this direction. So, you've got the PM resource page, and also there was a PM summit last month in Santa Clara that I went to. Very good. And that's where all this comes from. And there's an awful lot more detail out there about persistent memory solutions and what people are doing with it. And